So at this point we've covered three reactions of metals with different things. So metals with oxygen, metals with cold water, metals with steam. And we've used those reactions in the observations to try and put an order of reactivity from most reactive down to least reactive. And that largely works, but there probably is like a hanging out in your head in that it's not really a foolproof way of working out the order of reactivity. Like clearly from this you can tell from the observations potassium is more reactive than copper. But can you really tell that aluminium is more reactive than zinc or zinc's more reactive than iron? For a lot of the ones in the middle, you're not 100% sure from these observations that you're definitely ranking them in the correct order. There is actually a way of doing that and actually ensuring that you do know the correct order. And so one different style of reaction we look at in this topic, this final type of reaction we look at in this topic, it's a reaction called a displacement reaction. Now, we did come across displacement reactions earlier on this year in terms of halogens, and the idea of one thing reacting with the other. And we do exactly the same thing with displacement reactions of metals. Instead of just taking out like a metal reacting with oxygen and doing that for every single metal, we're now reacting metals with each other. Being more specific than that, we're reacting a metal with another metal compound and seeing if anything happens. So, going to use a simple everyday example before we look at the real examples. I might have used this example before. This is an everyday one. This is little Timmy. He's got a bag of sweets here, and here's Big Boris on the scene here. The question is, what happens in this scenario? So the answer is Big Boris wants those sweets. Because he is stronger, he is able to remove those sweets from little Timmy. If Timmy wants his sweets back, he's not capable of bringing his sweets back because he's not strong enough. So it's the idea that the strong or reactive thing is able to take something from the less reactive thing. A reaction we might look at is what is this? If I look at, try and make it simple, magnesium reacting with copper oxide. The question is, which one's more reactive? The more reactive one from your reactivity series is magnesium. Copper's least reactive. Using this analogy, because magnesium is the more reactive metal, it's capable of removing from copper the thing that copper's bonded to. So copper, the minute it's bonded to the oxygen, is quite happy like holding on to it. But because it's not as strong as magnesium, magnesium is very capable of taking that oxygen away and leaving copper by itself. So at the end of this reaction, we'll have magnesium oxide, that's now a compound, and copper by itself. The terminology we'd use here is that the copper's been displaced. Displacing as a word means pushing out. So magnesium has pushed the copper out of copper oxide and taken the oxygen for itself. If I imagine to kind of reverse that reaction, so copper trying to react with magnesium oxide, nothing is going to happen. Copper is less reactive than magnesium, therefore it's not capable of removing that oxygen from the magnesium or displacing magnesium. So there'll be no reaction there, you won't see anything. So the key thing is, in a displacement reaction, it's between one metal and another. A more reactive metal is able to displace a less reactive metal from its compound. So it's always that order. The more reactive one has to be by itself, the less reactive one has to be in a compound at the start, and then you see it displaced from that compound. And that's how we actually get our perfect order reactivity series. As you might imagine, we can actually do matchups of all the elements, all the metals in a reactivity series, and we'll actually be able to get a proper scientific order of what things are able to displace what other metals, and that gives us the correct reactivity series. Now there are a couple of specific examples to look at, and we'll look at them here, but in general you can ask quite a few displacement reactions, but as long as you know that kind of general principle of more reactive, less reactive, you should be able to cope okay. So the first one we look at is here on the bottom of page 6. In fact, before going on the example, just maybe look at that definition. If you're asked to explain what a displacement reaction is, you write this. A more reactive metal takes the place of a less reactive metal in a compound. That will get you the mark there. First example of this, you can do a displacement reaction between two solids. So that's an example of this. The two solids here are aluminium, that's the element, and iron oxide powders, that's the compound. This reaction's got a name, it's called a thermite reaction. It's actually used to make molten iron for things like fusing railway lines together. So it's got an everyday use, but we'll not worry about that. So let's play that through. We've got iron, we've got aluminium. Which one's more reactive? If I look at my reactivity series, it says aluminium is. So aluminium is going to be able to displace the iron from its compound. So if you think about the right hand side, aluminium's now got the oxygen, yep, it's ripped it from the iron, and iron has been displaced, it's by itself. If you're asked to put that in a symbol equation, it's no different from any other symbol equation. As soon as you got the word equation correct in your head, you're just converting all the words into symbols, and that'll get you the correct equation at the end. This case, I said it makes molten iron, which is quite useful. It produces a lot of heat, it's very exothermic, and generally all displacement reactions will be exothermic. That's an important observation. So that's not really one we do in the lab that much, but this next one is a very common one, and it comes up in questions quite a lot. So the first one we looked at was two solids reacting together. Another scenario for a displacement reaction is a solid metal reacting with a solution of a metal compound. That's probably the most common way of doing it. Again, might not be clear what I mean by that. Look at this example. Magnesium is a metal, it's going to be the solid. Copper sulfate, I could react as a solid, but it's easier often to react it dissolved in water. So I've got an aqueous solution of copper 2 sulfate, and if you remember copper 2 sulfate, that's going to be a blue solution. If I lather with a spatula some magnesium powder into my blue copper sulfate solution, I need to think about what's going to happen here. So there's a blank here, so we actually can think about this ourselves now. Your key thought process is this: which one of these metals is more reactive? Answer: magnesium. Therefore, magnesium is capable of displacing the less reactive metal from its compound. So if I think about what that looks like, it's going to take the sulfate away for itself. The products of the reaction are therefore going to be magnesium sulfate and copper by itself. Right, the symbol equation for that, again, I just convert all these words into symbols. Mg, go and give it its symbol solid. Copper 2 sulfate, Cu2 plus SO4 minus, all in the back of the periodic table, CuSO4. It's dissolved in water. Magnesium sulfate, Mg2 plus SO4 minus, MgSO4. Now it's going to be dissolved in water as well. Remember, group 2 compounds tend to be quite soluble in water. And then finally copper, Cu, is going to be a solid because metals generally don't dissolve in water that well if they don't react with it. So that's our symbol equation describing that reaction. The new thing here is the observations. Now, again, observations have been a heavy feature of this topic. With displacement reactions particularly, it's not that hard to work out observations just by looking at the equation. So it's not a case of rote learning hundreds of different observations or different reactions. What I mean is this: it's similar to how we looked with acids earlier on this year. At the start of the reaction, I've got solid magnesium. At the end of the reaction, I don't. It's in the compound. Therefore, that grey solid is going to disappear. First observation. At the end of the reaction, I've got copper as a solid, but it wasn't there at the start, therefore it's been formed. Copper looks like a red-brown solid, so red-brown solid appears. Next one is a little colour change. So if you think about copper sulfate, I said it's a very common one in this question because it's got a very distinctive colour. Copper sulfate at the start is a blue solution. Copper sulfate's not there at the end. Magnesium sulfate, think back to that wee checklist on the acids booklet, it's a group 2 compound in solution, therefore it's a colourless solution. So what we'd write there is that the blue solution turns colourless. And the final observation, I said, it's true for all displacement reactions. Generally, you'll make some heat, so heat will be produced. So there's generally 4, potentially maybe 3 if it hasn't got colour solutions, observations for displacement reactions. In most questions, you only need 2. So you've got plenty here to go off for the questions in the exams. So all we've looked at there is kind of 2 common examples of displacement reactions, but as I said, they could ask you a large list of variations of that. You have to sort of be able to cope with yourself. I also said that this is the proper way we'd actually work out the reactivity series. We use those reactions with oxygen, water and steam to guide us, but this is the proper way. And this little section we're going to now will demonstrate how that works. So let's imagine we've got these 4 metals: iron, zinc, copper, magnesium. Obviously, because we've looked at them already, we know what order they come in the reactivity series. But let's just imagine for now, thought experiment, we don't. So we don't know which of these is most reactive, which is least reactive. The proper method we'd use to definitively and confidently work out which one is most and least reactive is by a series of potential displacement reactions. So what we'll do is we'll pick one metal at a time. We'll start with iron, and we'll work out, or we'll make up solutions of the compounds of these other three metals. And what we'll see is iron able to displace any of these metals from their compounds? If iron is able to displace, we'll be able to say iron's more reactive than it. But if iron's not able to displace a metal, we'll know that it's not more reactive than it. So by kind of trial and error, we'll be able to work out what iron's more reactive and least reactive than, and we'll be able to overall work out an order of reactivity. So in this first set of experiments, I've got iron. I'm adding it to either zinc sulfate, copper sulfate, magnesium sulfate. Now, in an ideal world, we'd be in school doing this as a practical and you see it for yourself. But you're just going to have to go off what I tell you for now, unfortunately. So if I add iron to zinc sulfate, it doesn't react. Nothing happens, therefore there's no equation. If I add iron to copper sulfate, something will happen. What I'll see is this. I'll see a grey solid disappearing, that's the iron. I'll see a red-brown solid appearing, that's a copper. I'll see a blue solution turning colourless. We'll not worry about that too much for now, the colours get a wee bit complicated, but I'll also get heat produced. The equation for that would be this. Copper sulfate is being displaced by iron. The iron's making iron sulfate, iron 2 sulfate we'll assume, and copper. So that's a displacement reaction if we do it in real life. If I add iron to magnesium, nothing happens. So from that information I can tell iron is more reactive than copper because it did a displacement reaction, but less reactive than zinc, wasn't able to displace it, less reactive than magnesium, wasn't able to displace it. So it gives me a bit of information, haven't got the full picture yet, and need to do some other combinations. So let's say I look at zinc now. So I've got zinc metal by itself, I've got compounds of the other three metals I'm looking at. If I add zinc to iron, I get some observations. The grey solid disappears, another grey solid forms, so the zinc is going to disappear, it's reacting, the iron's going to be formed as grey solid, heat released again, and I get another equation with that one. So the zinc is more reactive obviously than the iron, so the displacement reaction is taking place there. If I add zinc to copper sulfate again, I get some observations and an equation. So we can assume the zinc is more reactive than copper because when we add it, the grey zinc disappears, copper is produced, it's displaced, heat's released, giving us this equation here. The sulfate's being removed from the copper to make zinc sulfate plus copper. However, when I add zinc to magnesium sulfate, nothing happens. No reaction, no observations. So from this information from these set of experiments, I can tell that zinc's more reactive than iron because it's able to displace it. It's also more reactive than copper because it's able to displace it as well. So zinc is more reactive than iron and copper. Next scenario now we probably have an idea of copper already, but again, let's imagine we didn't. So I'd get copper and I get three different solutions of the other metals to see if anything that copper can displace. However, in reality, copper does nothing with any of these compounds. The implication of that is that copper is not reactive than any of them, not more reactive than any of them, it's the least reactive. So copper is more reactive than none, Na. Final one, magnesium. Again, just to confirm what I think I know already. If I add magnesium to iron sulfate, zinc sulfate and copper sulfate, I get equations and observations in every single case. So we've got these observations. In each case, the grey solid disappears and we'll get an observation for solid appearing depending on what that is. So iron is grey, zinc is grey, copper is red-brown. In each case, heat released as well. And we've got our three similar looking equations. In each case, you're forming the magnesium sulfate because it's taking the sulfate away from the other metal, and we're releasing or displacing the less reactive metal. So from this I can work out that magnesium is more reactive than all of them, it's more reactive than iron, it's more reactive than zinc, it's more reactive than copper. Putting all those findings together, I can work out the overall order of reactivity. I know the most reactive clearly is magnesium because it displaces all three. I know that second most reactive is zinc because it's able to displace iron and copper. I know the third most reactive is iron because it's only able to displace copper. And I know copper is least reactive because it's not able to displace anything. So by a wee bit of kind of logical thinking, wee bit of trial and error, I can work out an order of reactivity for some unknown metals if I assume I don't know the order of reactivity. And the last thing to look at just for now is it's a common self question this. Now obviously you might think, but surely we always know what the order of reactivity is because we know the reactivity series. This question is a wee bit different and it's kind of similar to the style you get in the exam. They've given you a table of some potential displacement reactions that have taken place. As you might notice, some of the metals here aren't in our reactivity series. So silver's there and lead's there. So why they're putting those in is that you can't just rely on the fact you know the order of reactivity, because they might put an unusual metal in. I've seen cadmium in, I've seen nickel in, I've seen lots of different alternative metals put in these kind of questions. So you have to be able to understand what's going on here. All the question is for 2 marks. Using the information in the table, arrange the metals in order of reactivity, most reactive first. Just be careful you do the correct way around. A common thing to do, we put the wrong way around. So let's think about what's going on here. I've got the metals by themselves on the left hand side, and how this table works is I imagine putting those metals in a solution of the metal compound around side. So with this box here, I'm putting lead into copper nitrate. You see it's greyed out down the middle. That's because you would never put a metal in with its own metal compound. That doesn't make sense. It can't displace itself. So there's lots of ways of working out this style of question. The way I do it is just think, well, I'll work out the most reactive first and then see how I go from there. So zinc is most reactive because it does reactions with all the other metals. It goes number 1. Least reactive, I go to the other extreme, is probably going to be silver, because there's no reaction, no reaction, no reaction. So I put down there. Second most reactive, I probably would say would be, if I just check, probably be lead, because if you notice it reacts with copper and silver, it doesn't react to zinc. Zinc's most reactive, so I put it at the top. Then third most reactive would be copper. Copper doesn't react with lead, doesn't react with zinc, but does displace silver. So therefore I put it third. So you're trying to get the correct order from things that do most reactions down to things that do least reactions. Similar question here. We've got kind of more of like a logical sentence question. It says iron can displace copper but can't displace zinc. Magnesium can displace iron and zinc but can't displace calcium. It's almost like a wee bit of a riddle. Some true and false questions. Magnesium can displace copper. It's not a great question in that you already know the answer to this, but just going off the statements here. Can magnesium displace copper? Well, if magnesium can displace iron and iron can displace copper, it's pretty safe to assume that magnesium can also displace copper if it's more reactive than iron as well. So true. Is it true that zinc can displace calcium? Let's think. So iron can't displace zinc. That's not too helpful. Magnesium can displace zinc, but magnesium can't displace calcium. Well, if magnesium is more reactive than zinc, but magnesium itself can't displace calcium, you wouldn't expect a less reactive one to be able to. So zinc cannot displace calcium. That is false.